Okay. Okay. Can everyone hear me? Yep. And I assume on Zoom it's fine as well. Okay. So thank you. My name is Amir Safavi-Naeini, and I'm going to talk about the millimeter wave device efforts in my group. A little bit of how we got interested in it, and where it's going, and interesting directions that we're trying to go to next. So yeah, and thank you to the organizers. I guess technically I'm a co-organizer, but this was really a bottom-up effort, driven by people who are really interested and excited about the science other than me. So yeah, thanks for putting together this. So this work involves a large group of people, actually, in groups and projects, several groups and projects. And I'm primarily gonna, I'll touch on all these topics, but I'll primarily focus on our work on millimeter wave electro-optic conversion. It's very similar to what Christina actually spoke about in the previous talk. This is work that was led by Kevin Multani and Jason Herman in my group, in collaboration with Emilio Nani at Slack. There's also an effort to do microwave to millimeter wave conversion, and there's going to be a poster by Farhan and Kevin on this subject. In addition, we're trying to develop microscopy, impedance microscopy, scanning impedance microscopy techniques in collaboration with Judy in ZX's group for understanding condensed matter systems better and kind of leveraging some of the instrumentation that's being developed. So how did I get interested initially in millimeter waves? It really started with kind of thinking about the challenges in that are faced by current quantum superconducting quantum computing systems, and this is essentially this interface bottleneck. So if you're trying to build a quantum computer that you want to extend to maybe millions of qubits, so you can perform computations that are truly, non-trivial, then it's hard to imagine doing it all in a single fridge. So you start to need to have interfaces where you can distribute entanglement at high rate between different fridges. And there's efforts to do this with microwaves, kind of cooled pipes from Andreas Wallraff's group. But if you upconvert that information to a higher frequency, optical is usually the frequency that people think about, but also millimeter waves are higher frequency, then the kind of cryogenic needs and the rates at which you can do this information transfer drops by quite a lot. There's also a more kind of practical issue, which Christina also touched on a little bit, which has to do with the cabling. If we can find a more efficient way to bring in all of the microwave drive signals into these emerging quantum machines, then we can actually scale them much more easily. So this doesn't have to do with quantum networking. It's really using light, for example, to generate microwave signals inside a cryogenic environment. And if you can do that, I think that could bring the cost down significantly. You can have one fiber carrying wavelength multiplex, many different separate microwave signals, and you can use kind of emerging photonics technology similar to what's being used in data centers right now to split up that signal and generate microwaves, on your PC board at the different frequencies, so you don't need cables anymore. Actually, you can imagine a system where there's no more SMA cables. So I'm going to first talk about this networking. The physics of this networking goal and what are the challenges here. So specifically for transduction, we're trying to convert signals between two different frequencies. So you need a nonlinearity to change the frequency of the electromagnetic signal, and we basically need to balance two different requirements. So you have to have a large nonlinearity for this process to be efficient. Usually that involves using a lot of pump light. But you also want to have very low heating. And so a lot of pump light, typically generates a lot of heating. So the way that the field has addressed this problem is to try to find approaches where the kind of intrinsic nonlinearity is high, so that we can have less pump power, and at the same time really try to minimize all of the losses in the system, optical losses in particular, because optical photons getting absorbed, that's where the heating in the dilution fridge occurs and causes the most amount of trouble. So the very common mechanism across many groups and experiments is to use three-wave mixing. Here you imagine you have a optical pump field at some frequency. Then there's a three-wave mixing interaction where you can take one of those pump photons, generate a pump photon at a different frequency, and then also generate a microwave frequency photon at the same time. So depending on how you tune your laser or what parameter regime you're operating in, the kind of linearized interaction can either be this beam splitter interaction where you're exchanging microwave and optical photons, or it can be a two-mode squeezing interaction where you generate entanglement between the two excitations. The important rate is basically assuming that this optical cavity has a line width that's large, so you kind of adiabatically eliminate it. The important rate is the scattering rate, which tells you the rate at which you generate pairs of optical and microwave photons, or the rate at which you exchange them. So this is the rate that we're trying to maximize. And there's also, we can talk about cooperativity, but I want to kind of focus on that rate. So that rate also sets the bandwidth with which you're generating entanglement. So, if I have a certain amount of optical pump power in my device, I'm generating entanglement at that rate, but I'm also generating heating at a rate that's proportional to the number of pump photons, NP. Oh, I do have a cursor. Great. Okay. So, I can, I have the rate of entanglement generation. I have the rate of, I have a certain amount of power that's being dissipated in the fridge. I can divide rate by power, and I can get an energy. And so this is the amount of energy that you will deposit inside a dilution fridge for basically generating a pair of entangled photons or converting a photon from one frequency to another. And what's important is that the intrinsic loss, this is the optical loss, and the nonlinearity come in. There, you take the ratio, you square it. This is sort of like a scattering argument. You can get to the same conclusion. And it also scales with the frequency of the carrier field, of the optical field. So if you're working with telecom photons, this is on the order of 1 electron volt. So that's the amount of power you're dumping in the fridge. And if this is something that's going to happen inside a dilution fridge, we're going to be limited to microwatt scale powers. So the rate, which is basically this amount of cooling power that we have divided by the number of or amount of energy required per conversion, is just given by the ratio here. So what's really nice is that this formula is very simple. It just really depends on two parameters: the optical quality factor or loss rate and the strength of the nonlinearity. And so we can compare a lot of different systems together. Here I'm just plotting the optical damping rate versus coupling rate for a large number of experiments. And if I, if I look at a line where you can get a 10 kilohertz rate, this is that line. So if you're above this line, your rate will be less than 10 kilohertz. If you're below this line, you can achieve higher than 10 kilohertz, and so on. So basically the good region is here. You want to increase the coupling rate and reduce the losses to get higher rates. The other interesting thing is that, so this plot contains many different platforms. So it contains electro-optics, optomechanical, and some of the kind of bulk optomechanical experiments that have been done to date. The electro-optic results are bunched over there. So these results usually involve microwave resonator, some sort of a nonlinear optical material like lithium niobate. You put them together. If you make your system really, really small, the interaction rate goes up, but the loss rate also goes up because you have more scattering. So, fundamentally, the nonlinearity of the material determines where that blob is. Integrated optomechanical approaches are based on kind of a two-step process. So you generate entanglement between an optical photon and a microwave frequency phonon, and then you, using the piezoelectric property of a material, you can convert those vibrations at microwave frequencies into microwave photons. And so they generally have higher kind of achievable rates because optomechanics is stronger than electro-optics. And so these experiments kind of invariably look something like this. You have you try to localize the light field into as small a volume as possible. You localize the mechanics or the elastic vibrations into a very small volume, and then you have them interact with each other. And then there's approaches based on kind of larger systems where you have like a crystal of sapphire or silicon, and you're looking at bulk acoustic waves propagating here and interacting with photons through Brillouin scattering, basically. So that's one approach, and then the other approach is actually probably the most successful approach to date, which is the one taken by Conrad Leonard and Cindy Riegel's group, where you actually use a very low frequency mechanical system and use kind of a two-step conversion process where you convert between light and motion that's at the megahertz frequency, and then you have another converter that goes from megahertz frequency motion to microwaves. Okay, but so there's been a lot of progress in this field over the last decade, and despite all this progress, the numbers for those rates are still on the order of the theoretical limits for the rates that we can achieve are still on the order of megahertz, and in practice, people are talking about maybe hundreds of hertz types of rates. And so then the question is, what sort of rates do we actually need to realize these distributed quantum computing approaches? And you can assume that you have, for example, a small patch of a surface code inside one fridge and another patch inside another fridge. To do, you have to do some sort of a joint measurement now across the qubits that are on these two boundaries, and so we can try to estimate for this surface code that's spanning two fridges what kind of rate for entanglement generation we need. It's a very rough estimate. So this surface code has let's say it has a distance d, so there's d qubits on one side. And it takes every round of error correction, the speed at which you're eating up that entanglement is TQEC. It could be on the order of about 500 nanoseconds. And let's assume we're trying to encode like 10 logical qubits per fridge. Okay, so then we combine them together, we have something that's larger. So just from these kind of back of the envelope numbers, what you need is something like 1 billion qubits per second. So the rates that we need for this distributed system is just much higher than what we currently have for the current approaches. And so this was one of the motivations to looking at millimeter waves, because if you remember that E qubit number, it scales with the energy of the carrier photons. So when you go to millimeter waves, if you use three-wave mixing, so that the argument holds, just from that expression, your carrier photon energy is much lower, so you'd be dissipating less energy. Actually, you can do much better than what's in that formula. Yes. Sure. Mm-hmm. These are just imagine the Google system. So these are transmons in the surface code. Yeah. So basically, you need to have a converter that generates entanglement between these two, so that then you can do a joint measurement. Yeah. Well, this is the rate that you need for transduction between these two fridges to maintain, some sort of a error-corrected state that spans both fridges. Yeah, basically. Yeah. Yeah. Yes, Dave. I think it's well, it has to be bidirectional because, like, fundamentally it's unitary process. But I think yeah, the nonlinearity, at least in this argument, the nonlinearity has to be happening at the low temperature stage. And there's actually in Hong Tang and actually Michelle, they have work where they show actually you could go to a higher temperature stage and use the low temperature stage just as a bath to cool some of that process, and that could improve those rates by order of magnitude or two. Yeah. But yeah. Okay. Any other questions? Yes. Yeah. Yeah, it's the same one. So I guess you can have it distributed across multiple converters, but it just adds up. So yeah, so this could all be generated by one converter or 10 converters, but the power still has to be dissipated. Okay, so this is one interface problem, challenge, bottleneck, whatever you want to call it. The other one is maybe a little bit more boring. And I don't mean to insult John Teufel, but because they demonstrated this the first time a few years ago. But it's about using light to just route classical signals so that we can, replace all of these coax cables with just fiber, optical fiber, and just get rid of coax cables. And so focusing on this control wiring problem, let me just give you like a very basic idea of what's happening here. So at room temperature, we have a laser. The laser goes into a modulator, generates a pulse shape. That goes down into the fridge with a fiber, and then we have a photodiode in the fiber that detects that. It generates a current or voltage. And then we use that to drive the qubit. So instead of having a coax line coming from room temperature, the signal would be generated near the qubit. And so, like, let's say I want to do some sort of a gate. I would change the optical intensity in this way. That would get detected. It would generate a microwave voltage. It has some area theta, and that just causes a rotation of the qubit state. And the reason I have all these lines here is because this process of the light being detected has some noise associated with it. And that's actually a problem. So fundamentally, the precision of this quantum gate is related. I mean, it's going to be related to many things, but just in principle, we can get to a fidelity that's given only by an infidelity that's given only by the amount of noise in this detected signal. So this is where quantization of light becomes an issue, because unlike because here we're actually detecting the light with a photon counter effectively, and so it's not a coherent conversion. It involves detection, and so that because of that, the granular nature of light actually becomes important. And so if I look at that area that under that curve, that's proportional to the energy in the light field that generated that signal, which is proportional to the number of photons that were there. And just from Poisson statistics, assuming we're using coherent light, the variance of that photon distribution is given by the mean. So that means that we have an infidelity that scales inversely with the number of photons that are in that pulse. So if I have a power budget of a few microwatts and I'm trying to get thousands of qubits, I'll probably need like 10,000 cables or microwave signals. So that means per each one of these lines, you need to have something like a nanowatt. And let's say we have the world's most amazing photodiodes with the highest responsivity that actually allows us to generate large enough microwave signals with that 1 nanowatt. Yes.
I'm surprised by what you said because your control signals will be coherent state. So don't
So it is a coherent state, but it's being generated by photodetection. So the power efficiency of generating a microwave signal with photodetection is much, much higher than the power efficiency of coherent conversion because of the kind of quantum defect. So there's always like a 10 to the 5 factor because of the different energies of the photons. You can get to power efficiencies that are on the order of 1 in principle with just detecting optical photons. So we're trying to increase the scale of the system, which that's why we're going to photodetection. But then it has the noise. Yeah. So if we have 1 nanowatt per qubit, if you just run through the numbers, a gate is 10 nanoseconds. That means there's going to be 100 optical photons per gate, which means that this quantum noise limit for the gate infidelity is on the order of 1%. So that's not good. Like so in practice it'll be worse than that, but in principle you're limited to about 1% if you're trying to drive thousands of qubits with light fields. Okay, so that's the other kind of realization of limitations in using light to network or to control these superconducting systems. And so the sort of key insight is that moving to both millimeter waves and to higher temperatures, which is enabled by moving to millimeter waves, sort of solves both of these problems. There has the potential to solve both of these problems. And this is an experiment that Kevin did with his colleagues in my group. And I don't think you have a poster on this, right? No, okay. But it's been published already, I think. So basically we took a high-speed photodiode, we put it inside a fridge. We used that to generate millimeter wave signals, and then we could do even spectroscopy of these resonators of immortine nitride on sapphire that Kevin built, using the optically generated signals. So, in principle, this works. We had more noise. I won't go in detail on this, but the paper is published. We had more noise than would be predicted by kind of shot noise, basically, because we had to amplify the signal and we didn't filter it very much afterwards. So there was a kind of amplified spontaneous emission. And we also found out that the photodiodes, when you cool them down, their performance degrades a little bit. We thought that was from packaging. Yeah, so it's, there's definitely doing some of this photonics in a fridge. Again, we have to think about the packaging very carefully. That's going to be a theme of a lot of the technical challenges. So that was for the control wiring, and then for actual conversion, we looked at whether we can do very efficient conversion from microwaves to millimeter waves. This is possible. And yes. Yeah. Oh, well, I guess repeat the argument of, okay, so I guess what I was saying is that microwave to optical and optical to microwave are very challenging because of these limits.
No, but like, I'm just thinking the short ones.
Yeah.
So like the short ones, they will be there. So.
Yes. Oh, yeah, that's right. But we can, right. So, oh, because basically, yeah, that's the basically it's because if we operate at a Kelvin, we can have more power. So we just have way more photons. Yeah. It comes down to that. Okay, so if we want to do microwave to millimeter wave conversion, this is something we also studied a few years ago with Marek Fechel in my group. He's now at ETH. The main advantages of this we found was that we need a lot less energy for conversion. So sort of gigabit per second networks, at least at the level of the transducer, are possible. But we definitely found that we have to understand the kinetic inductance nonlinearity a lot better, because this approach was based on using kinetic inductance. And also, when we use a 4-wave mixing nonlinearity as opposed to 3-wave mixing, there's a lot of parasitic processes that reduce the fidelity of that transfer. You just have way more processes when you're doing 4-wave mixing than 3-wave mixing. And at the time, we didn't know about snails and ATSs and all these other nice circuits that have been invented. So now, if we just go from microwave to millimeter wave, you can actually have cables that are very low loss. Teflon, PTFE is very low loss at millimeter waves, and it can be used to transmit information. If you keep that cable at around 4 Kelvin, it can transmit information over tens of meters without any degradation, or with very little degradation. But we also, a lot of this technology still has to be developed. So these are primarily the challenges. The numbers are listed here. The main number is that the energy per qubit was on the order of attojoules. So that's about 6-7 orders of magnitude better than the best optical systems. And but we did have to, the conversion efficiency wasn't 100% because of all these other processes that we had to worry about. Okay, I won't go into detail on that. What I wanted to spend more time talking about is the kind of next stage of that conversion process, which is going from millimeter waves to optical frequency photons. And so this is in case you want to actually connect your quantum systems together with optical fiber, you still have to be able to convert them. And so initially we were thinking that this could be part of like a 2-stage converter. So you go from microwaves to millimeter waves and the millimeter waves to light. And the millimeter wave to optical converter would be at a higher temperature, so that you can just take a lot more optical power and it wouldn't be an issue. Recently, some of the stuff that Dave is going to talk about, there are now native millimeter wave quantum circuits, qubits, which is very exciting. So you could imagine actually having everything at higher temperature, and maybe that's the future. So let me just jump to the approach here. So we have a resonator. This is similar to what Christina was just showing. So we have a resonator, an optical resonator that has a large number of modes. And we pump, and so the length of the resonator is such that the spacing between these is around 100 gigahertz. And then we send a pump field on the resonance in the center. And the sideband transitions involve the RF photon. So that's like the concept. This is what the device looks like. So this is our ring, a racetrack resonator. It's made out of lithium niobate, which I thankfully don't have to explain what it is, thanks to Christina. And there's a small nitride dipole antenna that's placed basically such that its electric field is aligned with the crystal axis of this optical racetrack resonator. You can look at so this substrate is made out of sapphire. These are nitride electrodes. So these are the electrodes shown here. This is the cross section of the lithium niobate waveguide, and then we have a layer of oxide on top of the photonics to basically protect it. Okay, so packaging this was quite a challenge. I think Kevin probably spent most of his time on packaging. This is a microscope image of the device, so we actually glued fibers. It was very, normally when we do experiments, we have stages that bring in the fibers, but when you're dealing with millimeter waves, you really want to do the electromagnetic packaging so that it doesn't have a bunch of parasitic modes. And so basically we need to glue the fibers. We can't have kind of an open system. So this is the resonator. These are fibers that are glued onto grating couplers. This is the copper package that Kevin designed that goes at the end of the WR10 waveguide for sending in RF. So the waveguide comes in like that to excite the resonator, and the whole thing goes inside our 4K cryostat, which is shown there. Okay. So in this setup, we were able to demonstrate coherent transduction. Basically, we sweep a laser, we see our modes, we put a laser resonant with the mode in the middle. That's our pump mode. And then a really basic experiment is to send in RF power resonant with where the millimeter wave resonator is, and then take all that light, put it on an optical spectrum analyzer, which is just a fancy spectrometer, and that shows that we're generating sideband photons. So by knowing how much power we're sending in on the microwave and optics side, and taking spectra like this, we can infer what the efficiency is. And we see that as we increase the pump power, the efficiency, it's supposed to go up linearly, and it's going up linearly for a while, and then it kind of deviates from that linear slope. We think this is due to heating. So as you heat the device, the positions of a lot of the modes change around. And so you can get, at certain powers, things become slightly more resonant, you can actually have more efficient conversion. From this efficiency and from the properties, we can extract that G0 parameter. It's on the order of a few hundred hertz, 700 hertz. We have a couple of different ways of extracting it. And something that was really surprising to me was that we can tune the RF detuning, and we see that the bandwidth of the transduction, so this is efficiency versus RF detuning, we see that the bandwidth of the transduction is actually limited by the optical resonator bandwidth. So the Q of the optics is much, much higher than the Q of the millimeter waves. In fact, it's so much higher that the line width of the optics is smaller than the line width of the RF. And so this is actually kind of an interesting parameter regime to be in. There were some papers by Tobias Kippenberg's group and realm of optomechanics. They call this kind of a reverse dissipation regime. And one of the nice things about being in this regime is that if you pump on the blue side and you enter some sort of a oscillation regime, you get light that is narrower band than your laser. So and this is just related to the physics of parametric oscillation. So I thought that was interesting. So you actually make a real laser. You don't make you make an optical laser, not a millimeter wave laser, when you make an oscillator out of this. So the performance of this system wasn't as high as we had hoped, and we're just trying to understand why that's the case for future work. And one of the main things, and it's something I didn't show on the previous plot, I showed the really nice optical spectrum, but you can look at the millimeter wave spectrum, and the millimeter wave spectrum looks like this. So it looks really bad. In fact, it looks so bad that you may even think that, like, how do you know there's a mode there? How do you know there's an n-butyl nitride superconducting resonator there? It just looks like garbage. We can tune the temperature, and when you tune the temperature, you see that this scattering parameter for the microwaves follows this kind of redshift and broadening that you would expect from Matisse-Bardeen. And so but then there's all these features that are not changing with temperature. So now we understand that this is probably due to modes in the substrate of sapphire. So sapphire is actually a fairly high K dielectric, and we're using a thick piece of sapphire. So we developed a model where we can basically fit a number of modes and line widths and coupling rates to figure out, to basically fit the spectrum. So it's a complicated model, but it gives us good results across temperatures. So we have some faith in it. For future work, one of the things we want to do is just go to thinner substrates. So this is a number of modes that you have in the sapphire substrate. We're talking about tens of modes in the relevant frequency range. If we go to thinner substrates, we can reduce that significantly. So just beyond parasitics, we also found out that the devices still, there's basically a lot of small design changes that would improve devices and fabrication changes. We have to get rid of the oxide. Oxide is bad for the millimeter waves. The quality factors of the devices can be higher. So there's a number of things to improve. In general, though, the parasitics is a big issue. Packaging is a big issue. When it comes to millimeter to microwave converters, I think we really need to understand the nonlinear interactions that are happening in these magnetic inductance devices. Yeah, so these are the things that we're going to focus on. So I think I have a few more minutes. So I just want to talk a little bit about sensing. So a lot of the focus has been on or motivated by trying to scale quantum computers, transduction, interfaces, things like that. But millimeter waves are also really interesting for new types of sensors. And so we have a project, ZX's group, there's a poster on it, on trying to develop, use this millimeter wave instrumentation to develop millimeter wave impedance microscopy, and just try to answer basic questions in condensed matter physics and material science using these devices. And so for this particular experiment, what we have is a silicon photonic crystal. So it's a millimeter wave photonic crystal that's you can see the holes by eye, and it has a resonance, and we can put materials near that resonance and bring a probe nearby to excite it at millimeter wave frequencies. And this direction, I think one of the interesting things that it leads to is, we're trying to improve the signal to noise here, but we're also trying to make new types of measurements, maybe photon counting detection, trying to get around shot noise, for example. And so this, this kind of leads us to the question of, can we make good detectors for these types of measurements? Can we make things that get around the limits of phase-sensitive detection, get around shot noise limit for millimeter waves, and just more generally, how do we do photon counting detection? So just there's a very rough landscape of millimeter wave detection. So let's say we have a molecule or some material or some basic process related to neutrinos or cosmic rays, something, and it generates millimeter wave phonons and photons in our device, and now we want to detect these. So what are the things that we have available to us now? Well, one thing is we can detect we can use those high energy photons and phonons to generate quasi-particles, and then we can try to detect those. If we have millimeter wave photons, we can convert them to optical photons, or we can convert them to microwave photons. That's what this talk and technology I talked about here is about. So the idea is you do quantum frequency conversion, and for those two, we have good single photon detectors now. So for optical photons, everyone now knows about SNSPDs, commercially available. For microwave photons, there's a lot of recent work on single photon microwave detectors, which is really exciting. I won't have time to go into it, but this is one example from a group in France, which involves basically using a nonlinear qubit to do these measurements. It's a very clever approach. It involves a three-wave mixing interaction between a qubit, a buffer cavity, and kind of a waste cavity. And so by setting your pumps properly, you drive this irreversible process where photons coming in immediately go into a waste resonator and excite a qubit. And so then by just monitoring that qubit, you know if there was a photon that came in. So as an example, and this device looks something like this. So the question is, one question is, can we actually do this directly with millimeter wave photons? And some of the results from Dave's lab has me at least pretty optimistic that this is possible. The other thing is, okay, for the quasi-particles, you can try to detect quasi-particles using a qubit. It's one way to detect them. And squats are a technology that's being developed by Noah Karinsky here at SLAC. You should talk to him. I don't know if he's actually here, but the basic idea is that you generate quasi-particles by playing with the band gaps of different materials. You can amplify the number of quasi-particles, and then these quasi-particles basically become trapped in some lower gap material, and then you use a superconducting qubit, microwave frequency superconducting qubit, to detect them. And I think for phonons, this is really one of the only waves I've seen, which is very promising at this point. And the reason is because if we wanted to, the only other way that I can get access to these things, if I have a millimeter wave phonon, is to convert the millimeter wave phonon into a millimeter wave photon. And that's really hard. There's been some really exciting recent work from Hong Kang's group where they use piezoelectric thin films of lithium niobate. So you take a thin film of lithium niobate, you put electrodes on top. That actually lets you address these millimeter wave modes, sub-THz modes. But if you look at this carefully, these electrodes really only couple to one phonon mode in that structure. And this is a really small structure, but it's still, you have to make it fairly large for the capacitance to be appreciable, to be able to read out these modes. And so if you try to count the number of modes that you have in the structure, number of phonon modes you have in the structure, you take its dimensions, you divide it by the speed of, or the wavelength of sound squared or cubed, and you get something like 100,000 modes, and your millimeter wave photons only couple to one of those modes. So if you're not careful, on average, you're going to get a quantum efficiency of 10 to the minus 5 with that approach, which is not good. So this is the same parasitic problem as before, but now it's much worse because you're talking about wavelength of sound, not wavelength of light. There's approaches with that we've been working on developing phononic waveguides. So these are structures that really only have one degree of freedom that you can couple to. And something that's really exciting that I learned about recently was this work by Marco Loncard's group, which is basically an approach to getting very high frequencies. So by going to a material like diamond, you can open up phononic band gaps with standard lithography and fabrication approaches that are in that millimeter wave band. And so this is maybe one way we can get access to phonons of that frequency. Of course, diamond is not piezoelectric. So it still doesn't really give us a way to convert those into millimeter wave photons, but Diamond supports qubits. Maybe we can use those qubits to detect millimeter wave photons. Okay, so that's all I wanted to say. Yes, thank you to the people who did the work and the sponsors. Any questions? Yes.
Yes, for questions about the seminar based on software.
Yep. Yes. Your answer to your first question is yes. I think the second, the second question is yes. The first question is if you have, so for example, if we have oxide, silicon dioxide has a fairly low quality factor. It has a high loss tangent for millimeter waves. And so our goal was to try to get millimeter wave resonators that have very high intrinsic quality factor. So, but then, you know, for other reasons, we ended up having to actually put oxide on the interaction region anyway. So some of those, we lost some of those gains. But that was a motivation for using Sapphire. Well, if you put lithium niobate on silicon, doesn't work. Yeah. Yes.
You mentioned these modes in the Sapphire. They seem to have a large
Mm-hmm.
What resonances?
Yeah. So, and Kevin, do you want to take that question? Yeah. So it's packaged. So those modes can't really, they can't naturally radiate into the waveguide. So they're basically standing waves which are in the Sapphire. And they just can't go anywhere else because they're not mode matched to the mode of the WR10 waveguide. You basically wouldn't see them if you didn't have the cavity there. The n-butyl nitrate cavity. Another question? Okay, so I think we're late for lunch. I think maybe we can continue discussion at lunch. Thanks, everyone.